So sometimes when you talk to somebody who's at the beginning of learning calculus, it emerges that they're unclear why people are insisting that they use radians when they are differentiating and integrating trigonometric functions. And in this video, what I want to do is on this slide to show you very simply why your measure of angle will make a difference to the derivative. And then on the next couple of slides, we're going to go through the argument to show that if you use radians, the derivative of the sine function is the cosine function. And then finally, we'll conclude the video with giving you an exercise to calculate. So let's start off by saying, why does it make a difference if you use radians? So let's imagine, first of all, that you are using degrees. So if you're using degrees, what you get is that the sine function increases from 0 to 1 as you go from 0 degrees to 90 degrees. So let's look at the line that joins these 2 points, and we can work out, because we know their coordinates, this is at the origin and this is at 91 here, we can work out the slope of that dotted line. So the slope of the line is the height, the change in height that we have here. We go from 0 to 1, so it is 1, and divide that by this distance, which is 90 minus 0, so it's 90. So that is the slope. Now, I hope it's clear that this has got something to do with differentiation. It's something to do with the slope here. And in fact, you can see that there will be a point somewhere around here where the slope is actually going to be exactly this value. So the derivative of a point around here is going to have this value. And that's something called the mean value theorem, which you'll meet later in your degree. So let's now look at this. Let's say that we are going to use radians. So if we're going to use radians, what do we get? Well, the sine function again increases from 0 to 1, but it does it going from an angle of 0 to an angle of pi over 2. That's the right angle in radians, equivalent to 90 degrees. So if we are using radians, the slope of this line is going to be 1, because it's exactly the same change. The sine function goes from 0 to 1, divided by this distance, which is pi over 2. And writing it like that is horrible. So dividing by a fraction is multiplying by the reciprocal of the fraction. So that's just going to be 2 over pi. And that numerical value of that is something like 2/3. So it's very different to 1 over 90. And again, just as before, this is going to be the slope of the derivative around here. So I hope that argument makes it clear that whether you use degrees or whether you use radians is going to make the slope of the tangent line to the curve different. And all the results for calculus are only true if you use radians. And what I'm going to do on the next couple of slides is go through the argument in detail to show that the derivative of the sine function is equal to the cosine function if we use radians. So let's look at that on the next slide. So on this slide, what I'm going to do is explain why the derivative of the sine function is the cosine function, and we're going to see that this is related to some limits. So let's look at the definition of a derivative. The function f of x differentiated with respect to x is the limit as h approaches 0 of this difference, the function evaluated at x plus h minus the function evaluated at x, all divided by h. So we can't just put h is equal to 0, because then we would have f of x minus f of x. That would be 0, and we would be dividing by 0. And 0 over 0 is not well defined. So this is our definition, and we're going to have to think about the limits. So for a sine function, what we do is we just replace here f of x plus h by the sine evaluated at the angle x plus h, and then we subtract the sine evaluated at the angle x, all divided by h, and then we're going to think about the limit to get the derivative. So here we have the function evaluated at the sum of two angles, x plus h. So that means that we're going to need the composite angle formula, sine of x plus h, and that is, as I hope you know, it's a good formula to know, sine of x times the cosine of h plus the cosine of x times the sine of h. So now what we do is we're going to insert this into here. So our derivative is equal to the limit of the sine of x, the cosine of h, that's the first term, plus the second term here, minus the sine of x. So all we've done is put that into here. Now, when we look at this, this is looking complicated, but we have separated out the x and h dependence here. And we see there is a sine of x here and a sine of x here. So those two terms naturally go together. And I'm just breaking up this fraction as a sum of two fractions. So we have sine of x times the cosine of h minus 1. That's there, all divided by h, plus, and then we have this term, the cosine of x times the sine of h, all divided by h. And this is now how we're going to calculate the derivative. So we have the sine of x times this, and we're going to work out what happens in the limit as h goes to 0, plus the cosine of x times this, and again we want the limit, what happens to this as h goes to 0. And in both cases you can't just put h as naught, because you would have naught, because cos of naught is 1 over naught, and here sine of naught is naught, so you'd have naught over naught. We have to think about the limits. Now, the key result is if you measure h in radians, and we're going to show this over the next couple of slides, the limit here approaches 1. So this goes to 1. So we're going to get cosine of x times 1, so cosine of x, and the limit for this is going to vanish. So this term will vanish. So that means that the derivative of the sine of x is going to be naught, so that's not there, plus just the cosine of x. And that is that standard result. But this limit in particular is only true if you are measuring the angle h in radians, and we're going to show that over the next couple of slides. So let's look at a little bit of geometry on the next slide that we're going to need to calculate this limit. So the proof we're going to look at relies on geometry, and we're going to take a sector of a circle. So let's say that our circle has radius r, and let's say the circle that we're taking out of it, like a slice of cake, has got an angle h. Now, the area of the circle, the full circle, is pi r squared. And the share of it that we're taking with our slice here, this sector, is going to depend on how big the angle is. So if the angle was 2 pi in radians, we'd have the entire circle. So we would have the full area, pi r squared. And what we do is we take the angle and we divide it by 2 pi, and that is our share of the circle in this sector. So if you imagine that you had, for example, h is 0, that would vanish. There is no area as you shrink the angle to 0. And as you increase the angle to pi, you would have a semicircle, and pi over 2 pi is a half, and that gives you half the area of the full circle, just as you'd expect. So if we measure our angle in radians, that is the area of this sector. Supposing, however, we were to measure our angle in degrees. So I'm not going to use degrees in what follows, but let me just show you that it would make a difference. The area of the circle would still be pi r squared for the whole circle, but if our angle is measured in degrees, it's going to be h, whatever the angle is, divided by 360. And this factor of h over 360 is the fraction of the area of the entire circle that is in this sector. So again, you can see that this result and this result are different, and when we use this result for the area, we are going to get the limit that as h goes to 0, the sine of h divided by h goes to 1. So let's look at that now and show that on the next slide. So this is the limit that we want to show, that as h approaches 0, sine of h divided by h tends to 1. And to do that, I'm going to start off with a sector of a circle, and I'm going to, for simplicity, say that the radius of this circle, so the distance O to A and O to B, is 1. And OA is OB is 1. So what can we say about the other points? Well, what I've done here is I've dropped a perpendicular from B to the line OA. So here we have a right angle triangle, OBC. This distance is still 1, O to B, and that means that BC divided by 1 is going to be the sine of h, the opposite over the hypotenuse. So BC divided by 1 is the sine of h, and that just tells you that BC is equal to the sine of h. And in the same way, OC, this distance here, divided by 1 is the cosine of h, so OC is equal to the cosine of h. And the curved line that I've drawn here is an arc of the circle that has radius OC, so it has radius the cosine of h. So that tells you that the distance from O to D is also equal to the cosine of h. And we're going to need these distances in what follows. So the argument that we're going to use relies on something called the squeeze rule. And to give you an example of the squeeze rule, let me just think of a number. So, okay, I've thought of a number, and now I'm going to tell you that the number I've thought of is greater than or equal to 7, and it is also less than or equal to 7. So greater than or equal to 7, and at the same time less than or equal to 7. And I hope you don't think that you need telepathy to realize that I was thinking of the number 7. It's the only number that satisfies that. So what we're going to do is we're going to look at the areas of the three shapes in the diagram. So one of the areas is the area of this sector of a circle, and we have a formula for the area of a sector of a circle. We've just derived it on the previous slide. So that's going to be this, and you can see that this is less than this area of the triangle, the right angle triangle, OCB, and I'm putting here less than or equal to because you can see in the limit as h goes to 0, these areas will both vanish. And then we also have this third area of this sector of a circle, which has the larger radius, 1, that we've chosen here, and that in turn, that area is greater than or equal to the area of the right angle triangle. So we have these inequalities. So now, we know the formula for the area of a sector of a circle. So it is the radius squared, and the radius here of this arc of the circle is the cosine of h. So it's going to be the radius squared, so it's cos squared h, times the angle in our sector of the circle, and that's just h, and that's divided by 2. And that is going to be less than or equal to the area of this right angle triangle. And the area of a right angle triangle, you know that it's a half the base times the height. So it's a half, and the base of our triangle is OC, and that's the cosine of h, and the height of the triangle is CB, and that is the sine of h. And that area in turn is less than or equal to the area of this sector of the circle with radius 1. So r squared h over 2 is 1 squared, which I'm not going to bother writing down because it's just 1, multiplying h, so we have h divided by 2. So we have these inequalities, and what we want to do is explore what they tell us. So you see immediately that everywhere there is a factor of a half, and we can get rid of those by multiplying all the terms by 2, and that does not change the inequalities. So multiplying by something positive, there is no problem whatsoever. So let's just get rid of those factors of a half. Then what I also want to do is I want to divide everywhere by a factor of h. And the reason I want to do that is because if I do that, I'm going to get here sine of h over h, which is what we're interested in. But we're also going to have a cosine of h here, and I don't really want to have that. So let's divide everywhere by a cosine of h. And as long as our angle is small, then the cosine of h is going to be positive. So again, we don't need to worry about changing our inequalities in any way. So we're going to divide each term by h and the cosine of h, and that means we're dividing each term by the same positive quantity. So if we divide this by h cos h, we'll get rid of the h, and we'll get rid of one of the factors of the cosine. So we're going to get the cosine of h. And that's going to be less than or equal to, now here in the middle term, we're getting rid of the cosine of h, and we're going to get sine of h over h, which is exactly what we wanted. That's why we chose this division. And then in the final term here, we are going to get rid of the h again, and we are going to get 1 divided by the cosine of h. So this is our inequality, and we now think what happens as h approaches 0. So as h tends to 0, we obtain, well, the cosine of 0 is going to be 1, or is 1, and that's going to be less than or equal to the limit as h approaches 0 of sine of h over h, and that's going to be less than or equal to 1 divided by the cosine of 0, which is 1, so 1 over 1, and that's 1. So now we see that the limit that we want to calculate is going to be less than or equal to 1, and it's going to be greater than or equal to 1. So therefore, by the squeeze rule, which is very logical, we have that the limit as h goes to 0 of sine of h over h is equal to 1. There's nothing else it can be. Now, had we used degrees, then this formula and this formula would be different, and the limit that you would get would not be 1. Okay, so that's one of our two limits. If you remember, on the very first slide we had two limits that we needed to obtain, and you might be thinking that the second one's going to require some more geometry, but actually this result is enough to tell us what the other limit is. So let's just show that on the next slide. So in our initial argument, we had two limits. We needed this limit, and we said that this was going to be 1, and we've just shown why it is. We also needed this limit, and we said it would vanish. So let's see why it does. So we want the limit of this, and we're going to multiply it by a factor of 1. So we're going to multiply it and divide it by the same thing. And it's important to note that the quantity we are multiplying and dividing by is not 0. So h is a small angle. The cosine of h is going to be close to 1. It's going to be approaching 1 as h goes to 0. So we're multiplying by something similar to 2 over 2. So this is absolutely fine to multiply it by these factors. The numerator, if we multiply these two terms together, is going to be cos squared h. The cross terms will vanish because of the minus sign and the plus sign here. And then we're going to get minus 1. So cos squared h minus 1. And on the bottom, we just have h times, open brackets, all of cos of h plus 1, close brackets. So the numerator is minus sine squared h, because you know that sine squared h plus cos squared h is equal to 1. So we can rewrite the 1 as minus cos squared minus sine squared. Cos squared cancels, and we're left with this. Now, we know then that if we just factor out the sine squared into sine of h, which we'll divide by h, then we'll multiply it by sine of h divided by cos of h plus 1. We know as h goes to 0 that this limit is well defined. It's 1. So this factor is going to go to 1, and it's multiplied by this, which is going to go to 2 on the bottom, and in the numerator this is going to go to 0. So this limit is going to vanish, and that limit would also vanish in degrees. Okay, so that's both of the limits that we needed, and with that, with those two limits, our argument on the second slide is complete. We have proven that the derivative of sine of x is the cosine of x if we measure the angle in radians, definitely not in degrees. Okay, I think this is probably worth your while, if you've not seen it before, going through a couple of times so that you feel confident with it. Once you've done that, on the next slide, I will give you an argument or an exercise for you to try. So here's the exercise. Show that if you use radians, the derivative of the cosine of x is minus the sine of x. This uses exactly the same arguments and exactly the same limits as before. There is only one formula that is new, and that is you need to know the formula for the cosine of x plus h. Apart from that, you don't need anything new. So you should, I hope, be able to show that. And with that, I will stop this video.